Good morning. Welcome back to the states of matter, the gas state. Today we will see the most important in the molecular gases, that is called kinetic theory of gases. Some people say molecular theory of gases, or kinetic molecular theory of gases, or microscopic. Like there, so many names are there, but it is a kinetic theory of gas. Some few postulates which are very much required, and take it granted that is first. This is for ideal gases. First one. Gases consist of large number of molecules. For easy understanding, I will say that you large tennis court you take, some 100 balls, people are playing left and right without allowing them into the falling on the ground. By evening, everything is stopped. So all the gases, all the tennis balls are collected and can be kept in a small basket. What I want to say from this is, gaseous molecules in a container is very small, tiny, but if you are able to collect it, that will be a small volume will be occupied at the corner if they are in the solid shape. But otherwise, they are in the random motion. And compared to the flask or the beaker or container, the particle volume is very small. That is the first point. And that means they are compressible. A lot of empty space is available. That is from the deductions. Means conclusions are like that. Now, second possibility is ideal gas. There is no attractions between the two molecules. No attractions between the two molecules or two temperatures. The ordinary temperatures that will be they are in the random motion, and they are exerting the pressure on the wall. When hitting into the wall, we are getting the pressure. That is the second. And they are in the random motion, and so they collide with the other particles, and there is an exchange of energy from one particle to other particle, and these collisions are called the elastic collisions. And even the collision is between the wall and this, there is an exchange of energy only, but there is no totally loss of energy and all. That is another possibility. And they go all the around, so they exert the pressure equally, all the walls, all equal walls gets pressure. And there will be different for a particular particle also at different times the speed will be different because of the collisions, right? So you cannot find the independent speed, but it will be average speed, and you can find out it is not in a potential energy because of the gases having, it is in the kinetic energy only totally. And last one is it is temperature dependent. The more the temperature, the more the kinetic energy, or the increasing the speed. Okay, these are the some of the ideal gas postulates. Of course, there will be for the real gases, there will be some deviations and all. We will see in the later. Initially, we will write the equation. Okay, the equation for the kinetic theory of gases is PV equal to 1/3 mnurms square. P you know is the pressure, V you know volume, 1/3 anyway, M is the mass of the one molecule or of the gas, N is the number of molecules, and U is the RMS velocity. And now we will verify whether this equation will also support the other laws like Boyle's law, Charles' law, Avogadro law, and the Gaseous, Dr. All those laws we will verify from this equation. So far we have seen the equations. Now we will go back to from this equation whether we can able to this. That tomorrow we will see. Now today small problems we will solve some simple problems, but confusing in MSETs or VNITs, or sometimes even for the senior these things. It will be slightly confusing, but questions are simple. Okay, now there is a drain cleaner. In that there is an aluminum foil. Aluminum foil is reacting with, and caustic soda is poured on this thing. So there is a reaction between the caustic soda and aluminum. And aluminum foil weight is given as a 0.15. Aluminum foil weight is given as 0.15 gram at 20 degrees centigrade, and 1 bar it is reacted. So immediately you should know about the reaction, then only you can solve the equation. So what is that? Sodium hydroxide is reacting with alumina. Sodium hydroxide means not the pure sodium hydroxide, because all the time sodium hydroxide will be with some concentration of water. So that will be added water. So aluminum hydrogen gases will be liberated normally, and sodium aluminum NaAlO2. You can balance, or otherwise Na everything is balanced. The only thing is hydrogen is not balanced. So 3 by 2 hydrogen I can write, or everywhere hydrogen 3 only, and like this also write. You can use any equation. 2NaOH plus 2Al plus 2H2O gives 3H2. Like this also you can write 2NaAlO2, or anything you can use NaAlO2, or either of the equation. Okay, now so aluminum is at 0.515 grams solid, and the 20 degrees centigrade 1 bar after reacting with the hydrogen gas is there. Now he is asking that how much the ml of the hydrogen gas, this can be in the hydrogen gas is liberated. Now this is the equation, and we have the equation because it is a gaseous state. PV equal to nRT. Fine. P is given as one this thing. Volume is to be found out for hydrogen first. If you, but limiting agent is already there here with alumina. So first alumina volume you can find out easily in one step, and R you know, T you know. So P I am writing as 1 volume of the first I will find out the aluminum volume, though it is not directly this thing, equal to N. N is given as 0.15 gram. So if I am taking out the first equation, so the aluminum is given to 27 is the molecular mass, N is equal to 0.15 by 27, R is I am taking now 0.083, means late atmosphere units, 0.083 late atmosphere per degree per mole, and T equal to 293 because 20 degrees centigrade. So I will get some value. Now directly, because I am telling the one step I can do it. So this one, so PV, in the P also I have taken as a bottom you take. So now V hydrogen if I am taking, that is 3 by 2 times. One alumina volume is 3 by 2 volume, molar volumes. So multiplying with 3 by 2, you will get directly 0.15 by 27 into 0.083 into 293. Immediately you will get the value. Roughly, if you want to see, this is 383 and 15 calculate, you will get in the 0.8 3 by 2 also, no, 0.83 liters, so it will be some 0.133 into 3 into 3 by 2, nothing but some 0.202 liters you will get. So this small simple calculation you do it, one step it will be over. So remember all the time, either equation this or this you can use, and the molar moles you convert, then 3 by 2 moles of hydrogen gas is liberated. Right. Number 2 problem, what we will see, this will be right. It is a mixture excited by the 2 point methane and the carbon dioxide. Methane is given as a 3.2 grams of methane. 3.2 grams of methane. All the time you should know about the molecular formulas also, and 4.4 grams of CO2. These two are taken. Carbon dioxide in a container is 9 dm3. All the time confusion will be there. So 27 degrees centigrade. So what is given? Methane weight is given, carbon dioxide weight is given, and flask is 9 dm3 degrees. And what will be the pressure in Pascal is asking. So immediately you should know about this is the partial pressures of the these things. Total pressures you have to calculate. Total pressure means N1. Simple equation I directly will write. P total equal to, you know, N1 plus N2 recollect immediately. Okay, this is nRT, this is N, RT is RT. N1 is the methane and N2 is the CO2. Simple. So you will get immediately the answer. N1 you have to calculate, that is 3.2 by methane is 4 plus 12, 16, plus N2 is 4.4 by carbon dioxide is 2, 16 are 32 plus 12, that's 44. This is the N. R is, initially we will take it the 0.083 R, and T is 20 degrees centigrade by RT by B, forgot. 27 degrees centigrade is nothing but 300, and the volume is dm³ is nothing but liter, remember all the time, 9 liters. dm³ means decimeter cube. So that is the finally how much is coming. 32 by 16 equal to take just 32, it is a 0.2 to 16 jar, and 44, so it is a 0.1. Simple calculations are in C, and 0.083 into 300 by 9. This is the so many atmospheres. How much atmospheres you are getting? How much atmospheres? This is coming to the 0.3. 0.3 into 3. 0.3 into 300, 30 into 3, that is nothing but 90. 90, if you see, it is a very simple calculation he has given. 3 years become the 300 here. And here also 0.3, this you see 3, 10. Means immediately you can see calculate. So finally you will get only 0.83, 10 into 0.8083. Very simple calculation, no? 0.83 atmospheres. 0.3 atmospheres equal to 8.3 into 10 power 4 Pascal, because 1 atmosphere equal to 1 into 10 power 5, 1 liter, 1 atmosphere equal to 1 into 10 power 5 Pascal. So if I am taking it, this is point. Okay, very good. Next, so we'll see the one more problem. So here the pressure of the gaseous mixture is given. Hydrogen in one beaker, hydrogen is given as a 0.5 liter hydrogen and 0.8 bar. Volume is given and the 0.5 liter and the pressure is given. And another beaker, volume is given 2 liters and pressure is given 0.7 bar. And finally these two are added in one more flask whose volume is 1 liter. At all the temperatures are constant and vessel pressure is not given. He is asking this. This is in the one vessel, this is in another vessel, is both he is taken into the another vessel, both are hydrogen only. So very simple this thing, you know, P1 V1 equal to P2 V2 equal to P3 V3 at constant temperature. So now, but here both is added into this thing. So P1 V1 plus P2 V2 is added and kept in the P3 V3. P3 V3. This is P1 V1, P2 V2. These two together he has kept in the not P1 equal to P2 V2. It is P1 V1 plus P2 V2 equal to P3 V3. Now P1 is given as 0.8, V1 is 0.5, and second vessel P2 is 0.7 and V2 equal to 2 liters. And the third vessel V3 is 1 liter and P is asking P3. 0.8 into 5, that is nothing but 4. 0.7 into 2, that is 1.4. 0.8 into 0.5 is 0.4. Okay. 0.4 and 1.4, so nothing but 1.8. 1.8 equal to P3, means 1.83 bar. This is the third one. And now one more small density problem. And at 27 degrees, and at 2 bar pressure, the density of the gas is 5.46 grams per liter. dm cube actually given. What is the density at STP? Very simple. D equal to d1 equal to is given as the 1 by m RT by P or RT1 by P1. In another case, what we require is D2 is required, D2 which is required equal to 1 by m again RT2 by P2. So if you see D1 by D2 equal to, in the both the cases you will have the 1 by 1 mm R, and this will be cancelled. Finally what will be remained? T1 by T2, and P is also there, so P2 by P1. T1 by T2, P2 by P1 is D1 by T2. What we want? D2. D1 is given is 5.46. So into T2 is T2, sorry, only T. So T1 T2 is not there, only one temperature. No, T1 is there. T1 is the 273 and T2 is T2 is 20 degrees, 27 means 300 by 0.46 equal to D2 by D2 equal to 273 by 300 into P2 equal to 2 by 1. Find out D equal to there is nothing but 3 grams. Okay, thank you.